Okay, so this is going to be a walkthrough of the second question or section 2 of that first mock exam. So remember, when we're going to fill out our exam, we're going to put our ID number at the top, our 8 digits. If I could think of 8 digits and talk at the same time, followed by your initials. This is going to be page 1. All right, so we can name this section 2 if we wanted to. That doesn't really matter. It's going to get attached. This is going to be problem A. So if I read that question, a random sample of 29 employees at a large company have a systolic blood pressure checked. Summary statistics are provided. The table below assume that the systolic blood pressure of all U.S. adults follows a normal distribution with a mean of 122 millimeters of mercury and a standard deviation of 20 millimeters of mercury. Approximately what percent of all U.S. adults have a systolic blood pressure greater than 142? Now, again, in class I always made you write the probability statement in there. So this is the likelihood that x is greater than 142. We just introduced that variable of x, so that means that x is the systolic blood pressure of individuals at company. Anyway, we have to make sure that we draw a curve on this, so we're going to draw a picture. Although, well, I don't know, best to have that. I think I remember reading about the creation of graphs and diagram is not going to be part of that, but because you could be expected to do this on a word processor. But anyway, we're going to hold with what it has been. So that means we have a mean of 122. We have a standard deviation of, here's my 142. I'm trying to find the area above that. So I won't say the old way, but we could go ahead and find a z-score. Again, remembering things. It could ask you to interpret the z-score. So let's do that. That'll be observed minus expected divided by my standard deviation. So that turns out to be 1. So if, for instance, I did ask us to interpret a z-score, we'd say that the blood pressure of 142 is 1 standard deviation above the mean of 142 systolic millimeters of mercury. Okay, so it's your distance and direction. Remember, it has to be above or below. Anyway, it didn't ask us to do that. So if we wanted to, we could invoke the empirical rule. And we know that, again, it falls at 1 standard deviation. So I know that 16% of my data lies above one standard deviation. So we could do that. We could also know that we could do a normal CDF. 142 is my left boundary, 1E99 is my right boundary. We're going to have a mean of 122 and a standard deviation of 20. Remember, if we're going to use a calculator, we're going to use that calculator speak. So this is going to be my lower boundary, my upper boundary, my mean, and my standard deviation. Okay? Although that was, yeah. Anyway, that turns out to be, back to my calculator with us, 0.15 or 0.1586. Okay, or 15.86%, whichever way you want to look at that. All right. So now we're going to roll on to question B. Describe the distribution of systolic blood pressure for the 29 employees of this company that were sampled. Is the max blood pressure of 175 considered an outlier? So this actually probably, this is me editing this problem. They're not going to probably ask you 2 different things on one letter. However, I wanted to get that in there, and this was a PDF file, and I didn't want to rearrange a bunch of stuff, so I just added it in there. Anyway, describe the distribution. So remember, when we describe a distribution, all right, we're looking for shape, center, and spread. All right, those are the 3 things that we have to address there. Your shape. Okay, we have a sample. This is where we're talking about the mean blood pressure. So with a mean, and we're talking about shape, it's approximately normal if my sample size is greater than 30. We struck out there, 29. Okay, if my population is approximately normal already, and that's what we're going to go with here. The shape is approximately normal because population is normal. Okay. The center, and again, your center of your sampling distribution is going to be the center of my. So the center of my sample is going to be the same as the center of my distribution up here. So it's going to be 122 millimeters of mercury. And lastly, we're going to have a spread, which is going to be the standard deviation of my sampling distribution. And again, because it's we're going to change that. My sampling distribution gets narrower And even if you forgot, and again, my formula sheet is probably buried in a pile somewhere that is horribly inaccessible, but we can kill time and find it. Okay, so here we go. We're going back to a random variable for a population. We're going to take that standard deviation and we're going to divide it by the square root of n. So again, make sure you have that formula sheet copied off. Anyway, I did that somewhere, except I don't know why I threw a 20 in there. Oh. Okay. That's if, I don't know what that turns out to be. That turns out to be 3.25. So this is where I'm going to have a parallel solution, which is bad. I'm going to scratch this out. It gave me my mean was, gosh, I'm going to have to start this over again. No, I'm not going to start it over again. This is the mean of the sampling district of the 29 employees. So the standard deviation is actually back to that chart where it says 17.5. So again, this is going to be the mean of my sampling distribution. So I'm just going to, this is me disagreeing with the person that put this key together. I think it's going to be this. I am going to just roll with that. Okay. This is a sample of 29. So yeah, I think I'm gonna roll with that. I'm gonna stick on that, even though I know it's in my description or in that box. If we go over here to the box, it says my mean is 139, my standard deviation is 17.5. Another thing to look at, my mean and my median are very close to each other. All right, so that is another mean that's another way we could have shown that that was approximately symmetric. We don't know about if it's approximately normal. That's why we went with that. Okay. Oh, then we also have to do the outlier. So remember, an upper fence is calculated by going quartile 3. We're going to add on 1.5 inner quartile ranges. Okay, so quartile 3 turned out to be 156 from that chart. My inner quartile range is going to be the difference between 156 and 124.5. So we're going to calculate that, and I didn't do it, so sorry. I was supposed to do that earlier and forgot. 203.25. So the answer to the question is the max, which is 175, is not an outlier. As fence is outside, above max value. Okay. All right. So we conquered B. Sorry, a little hiccup in there. If I knew what I was doing with the video, I'd go edit that out. Well, we won't test my abilities today. All right, moving on to C. Part C, the company CEO wants to know if the mean systolic blood pressure at a company is higher than the national average. State your hypotheses for testing this concern. So again, it's not having us actually conduct a test. It just wants us to write down, if we were to conduct a test, what would my hypotheses be? So we can go with what we expect. That would be the mean is 122. However, we believe that our company is higher than that. We're going to go with greater than 122. And we introduced the variable there, so we have to define that variable. Mean is the true blood pressure of employees at the company. All right. D. The conditions for the hypothesis part were satisfied. Hypothesis test resulted in a t-score of 5.495 and a p-value of 3.591 times 10 to the negative 6. Interpret the p-value in the context, and then what would this p-value lead us to conclude? All right, so remember, now it comes back to those definitions. We didn't hit definition of a p-value too hard, so again, let's try to understand what we're doing there. So if the null hypothesis were true, we can expect to see a mean blood pressure. No, so the likelihood of seeing a mean blood pressure greater than 142, 142 or greater, let's do it that way, is 0.000003591, or very unlikely. Since the p-value is less than any usual value of alpha, or 0.05, we will reject the null. There is sufficient evidence to suggest the mean blood pressure at the company is greater than 122 millimeters of mercury. All right, so we got that one covered. All right, where is part? I haven't been doing a very good job of following the questions. Here we go. E, explain in context what it means to make a type 2 error, okay, in this situation. So there's not enough room here. So again, we're going to pull that up the top. We're going 1, 2, 3, 4, 5, 6, 7, 8, and PD. And again, if you had those filled out ahead of time, you could have saved yourself 10 seconds and did that. It had me write that down. And again, this goes back to, you remember trying to turn in something that is legible for a reader to read. So I know you're going to be feeling like you're in a hurry, but don't be sloppy with it. Okay. So we're on page 2 now. We're going to answer part E. Okay. In part E, again, explain in context what it means to make a type 2 error for the hypothesis in parts C and D. Okay. So a type 2 error, in a type 2 error, we would conclude that the mean blood pressure for the company is not unique when it actually is. We conclude blood pressure is not over 122 when it is. Okay. Now this doesn't say anything about a consequence, but just in case, it, again, who would stop here? That's all it asked me for. Although I would assume that it would want you to do, explain a consequence. So the employer may not start screenings because there doesn't appear to be a need. And so the problem actually had nothing about screenings in it. So that was just, probably me putting more into it. But that's where we were. Okay. All right. Scrolling on down. So again, 3 more questions to answer about this. Okay. They gave us, in addition to recording the systolic blood pressure of the 29 employees, their ages were also recorded. A linear regression was fit to the data. Graphical and numerical summaries of the analysis were given. Use the information to answer the following. So, F, we want to interpret the slope of this regression line. Okay. So for every increase in, again, this is my explanatory variable, and if we look at that, look here, my explanatory axis is age. So for every increase of 1 year in age, the, again, we may make sure we get those keywords in there, the predicted blood pressure will, actually systolic blood pressure will increase. And we knew it was going to increase because my slope over here is a positive 0.9493. Will increase by 0.9493 millimeters of mercury on average. So again, we either need to have on average there or by about, just to be fuzzy. Okay, we're not going to be non-deterministic language. That's what we're trying to write here. All right, moving on to G. Comment on the strength and direction and form of the relationship between age and systolic blood pressure. Okay, so again, we need to know what R is in order to do that. R is going to be the square root of 0.712, and that pulls out at 0.844. So again, it's direction, form, and strength. All right. Is what we're shooting for. Okay, so, and again, context. All my answers have to have some type of context. So the relationship between age and systolic blood pressure is positive, okay, because it's going to be a positive R value, or actually it's a positive slope. But that was, again, we'd go look at that slope. Sometimes if we had a decreasing relationship, this R value may be negative, so always go back to your slope and look. Okay, it's positive, it is likely linear, and it is strong. H. Is the linear model appropriate here? And again, this is just, I extended that. The other person answered it within that question, but it is linear. Linear is appropriate, and why is it appropriate? Okay, because residual plot shows no pattern. Okay. All right. So that wasn't too bad. 18 minutes. Again, that's supposed to be a 15-minute question, and I talked some more in there. Had that brief pause. So there you go. Have a great night.